Neural networks interacting with physics simulations is something that I find very interesting. I did some experiments in the past with neural networks controlling drones, rockets, or with my Predators vs. Prey videos. In this video, I will try to make neural network control a very simple creature to make it walk. The physics simulation will be implemented using a basic Verlet solver. If you want more information about Verlet and the possibilities it offers, you can check my previous video on the subject. To interact with the simulation, the creature will have a minimalist body. First, we will need some bones to create a frame for the body. These bones will be implemented using a simple distance constraint. The 4 bones are connected in the center by a common joint point. In order to generate movements, we need to add muscles connecting adjacent bones. These muscles are actually springs with a fixed strength and which rest length varies with contraction. Next, the creatures will have 4 feet with controllable friction. Then I added some sort of skin on top of the structure and nice eyes to differentiate front from back. Under the hood, each creature has a neural network in charge of controlling the muscles and the feet friction. Here are the inputs and outputs of the network. I didn't represent the hidden nodes as they will be generated as the training progresses. Everything is ready. All that's left to do is to train them. The training consists of 3 stages: the evaluation, the selection, and the mutation. During the evaluation phase, agents perform tasks and get a score that reflects their performance. This step was way trickier than expected. My initial approach was to generate a random set of points in a square map. Then, the agent has to reach them one by one to get as much points as possible in a limited time. However, I noticed something weird. A lot of the agents would only turn in the same direction, even when the other one is clearly faster. I did some stats to check if my training setup was right, and I came across an unexpected result. It seems that with this configuration, the probability of having 2 turns to do in the same direction in a row is higher than 50%. It is around 61.6%. This result remains true if the map is a rectangle or a circle. I have no strong opinion on the cause of this result. To remedy this problem, I then tried another configuration. When the agent reaches a target, it is teleported back to the center of the map. I also switched to a circle to ensure that the point distribution is the same in all directions. After these changes, the problem almost vanished. A very important part of the training is the fitness function. This function describes how the interaction of the agent with its environment influences its score. A very straightforward approach is to give agents 1 point each time they reach a target and nothing the rest of the time. This function is very simple to implement and doesn't introduce bias in the process, because the developer doesn't give its opinion on what is a good way to solve the problem. However, it is also very slow because agents have to figure out what to do without any guidance. Another approach would be to give some hints to help the selection algorithm knowing which agents are doing better even when they didn't manage to reach any targets. With this function, we also increase the score as the agent gets closer to the target. The A coefficient has to be manually set. It has to be order of magnitude smaller than the target reward, or agents will tend to get as close as possible to the target without touching it to optimize their score. I decided to use this function because it offers much faster progress of the agent, even if it can be more complicated to tweak correctly. The aim of the training is to create a new generation that will perform better than the last one, to iteratively improve the performance of the agents. To do so, we start with the existing generation, each agent having a score from the evaluation stage. The population is then sorted and the bottom half is discarded. The top 10% are kept without any modification. Then, all scores are added up and adjusted so that the sum is equal to 1. If we choose a random number between 0 and 1, each agent has a probability to be picked which is proportional to its score. To create new agents, we generate a random number and pick the corresponding genome. We then randomly apply some mutations to it. These mutations can be a new connection, a new node, or a modification of existing connections. This process is repeated until the new population is full. This new generation will then be evaluated, and so on. To highlight the different creatures' walking patterns, I added sound-like particles on the map, using the solver I have presented in a previous video. I ran multiple training sessions with 10,000 agents for 1,000 iterations and got vastly different and interesting strategies. First, let's see the progress made by the agents during one of these sessions. I was very surprised by the convergence speed of the agents. In a few iterations, most of them were already able to move quite easily. I will experiment with bigger structures containing more bones and muscles. Thank you for watching.